Now, once we know the rates of change of f along a given direction s, I can talk about estimating what the function will look like as I move along direction s. So here we use a very useful and elementary result called the Taylor series, which helps us in approximating any given function which is differentiable. So what Taylor series says, let's look at the 1D case first. So suppose I am at a given point x1. So and we want to move to the point. So we want to approximate the function at some distance away from x1. So now, since we are in one dimension, there are no real directions to move. I can only increase x1 or decrease x1. So let me say I change x1 by alpha. So what will be the value of the function f without actually evaluating the value at the new point? And I need to find this approximation so that I can move in the right direction and take the right step length. So what the Taylor series tells us is that fx1 plus alpha is exactly equal to the value at x1 plus some estimate on the basis of the first derivative evaluated at x1 plus some contribution from the second derivative evaluated at x1 plus the third derivative, and so on and so forth. It's an infinite series, but it may happen, for example, if f is a polynomial function, then the higher order derivatives may eventually become 0, and it might end up being a finite series. So if you don't know any derivatives, then the first cut approximation for fx1 plus alpha is fx1, which is quite intuitive. If you don't have any information, then you would pick the same value as the point value you know. But if you know the value of the derivative also, then you might want to use this as an expression approximation for this. So the first order approximation is and this is a constant term. This is also a constant. And we have a linear approximation in alpha. If we look at the second order approximation, then I will take terms up to the second derivative and ignore the rest. And this is nearly equal to this because I am ignoring rest of the terms, but the theory tells us that as we take more and more terms, the remaining portion actually falls pretty rapidly, and our approximation becomes better and better as we take more and more terms. So in practice, usually this quadratic approximation is usually pretty good, especially if alpha is not too big. If alpha is very big, then you might need many more terms. But for our algorithms, we will be happy going up to second order. Even there, things will get a little complicated because we are not in one dimension. Okay, so we would like a general Taylor series in n dimensions. So given a point x1 which is a vector f x1 plus alpha s. So again, alpha is a scalar, s is a direction of dimension n. This is value of x1 plus alpha times s transpose gradient of f. So instead of the first derivative that we wrote for one dimension, now we have to use a derivative in n dimensions, which is the gradient. Similarly, for the second order term, we need the Hessian. Plus, I'm not even going to write the third order term because it is quite complicated. I don't even know the right way of writing it, because if I look at the third derivative of f, it is going to be a tensor in 3 dimensions, because you have to divide, take the derivative with respect to every triplet of dimension of components of x, which is going to be a 3-dimensional tensor. So a quadratic approximation of f is going to be just these 2 terms. The function value, the gradient term, and the Hessian term. And the linear approximation would be just these 2 terms. So we'll stop by looking at the geometric interpretation of this Taylor series. So suppose I have a function in one dimension. My current point is x1, and I would like to estimate the function value at x1 plus alpha. If I just take if I ignore the derivatives entirely, then my estimate would be this. If I look at the first derivative, then I will be slightly closer there. If I look at the second derivative and use this approximation, so this is my first order approximation of f, and you might see that in the neighborhood of x1 this is fairly okay, but as you go far away it loses closeness to f. If I take the second order approximation, it might be slightly closer and better than the first order, second order or quadratic approximation. So in the neighborhood of x1, the quadratic approximation would be a little better than the first order approximation, and as we go further away, it might still deviate quite a bit. In higher dimensions, you will need contours to look at, to understand what this might mean. So recall that if I have a function in two variables, x2 and x1, then I can draw some contours along which the function is constant. If I look at the linear approximation of the function and draw its contour, say at this point, then the linear approximation might look like this. The contours of quadratic approximation, this is a very rough cut picture. Might look somewhat like this, I might be wrong, but at that particular point, at x1, both linear and quadratic approximation would have the exact same value, and that you can see from this expression. If alpha is 0, I don't get any of these terms, and fx1 would be exactly same as fx1. So at the given point, both linear and quadratic and even higher order approximations will give me the exact same value, and at higher alpha values, depending on alpha, it might be a good approximation or a somewhat not so good approximation. So once we have this approximation of f in the neighborhood of x1, I know how the function looks like in the neighborhood, and then instead of minimizing the actual function, I can minimize this approximation, or I can choose a good S based on this approximation. So this we will see a little bit later. That's it for now, and bye bye.